Hello everyone. I just want to get you a little bit primed for the voltage or electric potential due to a point charge and help you get problem 11 on chapter 19 homework 1 done, because while many of you looked in the book and found the formula, maybe an understanding of where that comes from is worth doing first. When we initially opened up the discussion of electrical potential energy and electric potential, volts, we did so using a parallel plate capacitor situation where you have a field that's uniform, constant field. In this case, I just threw a number out there, 2,000 newtons per coulomb. But the field is constant. And so a positive test charge Q naught experiences a force if it is allowed to move from point A to point B. That force does work. And the force is the charge magnitude, Q naught, and E is the electric field strength. That's the force. The work, of course, is force times distance, so it's QE times the distance. We're going to use R in this chapter. This is force times distance. What is kind of and that work represents a change in electrical potential energy. We then defined the difference in potential, electric potential, which is the potential at B, the final potential, minus the initial potential at A. That we defined that as the change in EPE that occurred due to the work done by the field per unit charge. A couple things I'd like to point out, and then we'll get to the voltage due to a point charge. One is that E, the electric field strength, you may recall from chapter 18, is KQ over R squared. When we multiply by Q here, we sort of get back our Coulomb's law QQ, because that is Q times E, which is force, which is KQQ over R squared. But when we multiply with this other R here, we lose the square on the denominator. And it becomes the electrical potential energy, EPE, is KQQ over R. There's a lot of K's and Q's and R's, and I'm hoping to give you a way to kind of make sense of them. Now, the difference in potential, electric potential V, could still be found by the work and then divided by the test charge you're moving and doing work on. So let's just place an arbitrary test charge here at point A. Say it's 3 microcoulomb test charge, positive always. So in moving it from A to B, there is some work. And we define the voltage as the negative of the work from A to B divided by the test charge. And of course, that's just the change in EPE divided by the test charge. But here's the problem. Because the field around a single charge, point charge, in this case the 1.5 millicoulombs, that field represented by those lines I just drew, that field is not constant. It's not like a parallel plate capacitor. And so the force, as you move it from A to B and you do work, the force is dynamically changing. The force is not constant. So you can't just multiply KQQ over R squared times R. It just, you have, as R is changing, F is changing. And so you need integral calculus to arrive at the solution. While that is beyond the scope of this course, there's a little paragraph in the book. And on page 564, they say, recall from chapter 6, work and energy, that you can only use force times distance to calculate work if the force is constant. However, with the eta of integral calculus, it says it can be shown that the work from A to B is simply KQQ over RA minus KQQ over RB. Again, remember, why is it KQQ over R, not R squared? Just a little reminder that work is force times distance. The force is KQQ over R squared. And when we multiply by R, that's where, I just showed you a moment ago, that's where that R cancels, the square. And so you're left with work is KQQ over R, as is electrical potential energy. A moment ago, I had this as work per unit charge. That's going to be the voltage. But the work is this, okay? This is the work from moving the charge from A to B. Because voltage is work per unit charge, the difference in voltage, we need to divide out the test charge. And in doing so, we end up with KQ over RA minus KQ over RB. Now, much like electrical potential energy is always relative to some reference point, it's really meaningless to talk about the voltage at a particular location without having a reference point. However, we can say what is the potential at point Z right here. But that's the potential compared to infinity. In other words, let's let Z be point A, and allow infinity, or very, very far away, to be point B. If this is very, very large, or tends toward infinity, then this whole quantity goes to 0. And so now we have the potential, due to a point charge, is just KQ over R, R being the distance from that point charge. So as much as this wasn't the prettiest thing, I hope I got you to this point, which is the potential due to a single point charge is KQ over R, where R is the distance away from that point charge, Q is the point charge, and K, of course, is the electrostatic constant, 9 times 10 to the 9.